Recording now.
It was just not been. It's frustrating.
Yeah, and those stairs are weird. When they put the business building in, they didn't have to put that stuff. They would have a perfect view of the peaks from the engineering building. They didn't put all that stuff on the top floor, and all that top floor is like the mechanical.
Is it really?
Yeah.
Huh.
The fifth floor is just, there was no reason for that.
I mean, a lot of the inside of the building is empty space anyways, just for that big lobby. And
Yeah.
stairwells you can look down.
Yeah,
Yeah.
It's like more aesthetic than functionality.
Yeah. Okay, so project 5 was due today. Your final exam is optional. Today I'm going to try to prove to you actually learned something this semester other than, I don't know what. Other than other things.
Fowler is difficult to work with.
Al Fowler is difficult to work with. I went from working for Al Fowler to Dr. Payne. I've worked with a lot of difficult people in my life. I have that skill. I grew up with the world's worst, most difficult person in the world, my brother, who was 16 years older than me. I was the youngest, so I was the baby. I had to be, everyone else had to serve me. As long as I could get Bucky to be on board with that. I'm used to working with difficult people. He kind of ran things while my mom was off doing stuff and my dad was off doing stuff. So the final exam is optional. It is Thursday, April 29th from 12:30 to 2:30 p.m. in this room. Or if you want to do it by Zoom, you can log into Zoom. Open book and open notes. There are 5 problems you choose 4. Covers everything for this semester. Do your course evaluation receipts. There's still a few people who haven't. They're due by Sunday. That's when they close them. Yeah, IEEE, we can't do anything because of reading week. We'll try to start it up again in the fall when people can actually go. The Philosopher's Writing Code comment is actually from an actual hackathon we had a couple of years ago. This guy thought it would be a really good idea to bring honors college people to our hackathons, building things with Arduinos. And there were philosophy majors.
That was when Joe was president, right?
Yeah. Okay. They wanted to get the honors college involved for some reason, instead of just having it be a regular. It was the officers. It wasn't me.
The dean of the honors, I think Joe's reason was the dean of the honors college was willing to give IEEE funding.
Yeah, but we have money. We don't have to rely on. We've got real funding. We've got corporate sponsors. If I want something, I go out and ask people for it. Much like my brother. Okay. This is Dr. Brower, and you've probably heard me grouse about her occasionally in the past couple of years.
I've never actually seen a picture of Dr. Brower.
But yeah, she is it took me a long time to find this too. The original creator of this class, who I often grouse about because she really thought through things in a different order than I did. But without her work, this class may have never happened. I would have never thought to teach a class just on memories. I would have probably taught a class like 490 in the fall. And she did teach. She was Brian Calloway's teacher, and Brian Calloway funded our road trip up to Micron. So a lot of background there.
I'm sad that you won't be active this summer. I don't get tickets for Micron.
Yeah, it was a little complicated though. And I left these in here just in case it ever happens again. Micron field trip for future reference. Ever in case you need to fill out and sign your permission slips and your non-disclosure agreements. Matt and I have successfully learned how to roll a band.
Yep.
We needed a third driver because we were going all the way up to Boise. And I couldn't go on the trip up because my nephew was getting married the week before in Saskatchewan. Yeah, things have started to clear up. The band's reserved and paid for. Where are you guys meeting?
We were going to talk about things we learned in this class. And here we are.
Right, yeah, here we are, just off topic again.
The final is a quiz on,
How to get to Boise with 8 people.
yeah.
But Micron paid for it all, and it was a really good trip, and they put us in a really nice hotel. And there's a lot of microbreweries that we found in Boise. We met Will Ritchie for a beverage night, if you remember Will Ritchie.
Name sounds familiar.
He's the guy who grows strawberries. He did an IEEE presentation on it. Okay, anyways. And there is all of this up at Micron in front of the secret building.
That's gonna help it. It's not.
So, Amy Allen, Chief of Staff at Micron. Yeah. People were really impressed because they wanted to go, and the people who worked at Micron wanted to go in the secret building and find out what was there. And we were the only ones that were allowed. Final exam is optional, open book, open notes, 5 problems, you choose 4, kind of like the midterm. Things we've talked about this semester,
Yes.
not the complete list. DRAM, signal integrity, semiconductor physics, flash, MRAM and ReRAM, and CMOS imagers. This is more likely like stuff you might see on the exam. There are different types of memories. There are biological memories, non-semiconductor memories like hard drives. This was mainly focused on semiconductor memories, DRAM, flash, imagers, ReRAM, and MRAM, but there are other types of even semiconductor memories out there. Ferroelectric RAM is one that is in the early development stages. We haven't talked about a lot, and some of this is just old.
Hopefully we'll find more about it in the future.
We will find out more. You'll find more about lots of things in the future. So okay. So this is SRAM. And the problem with SRAM is SRAM takes up 6 transistors. It's amazingly fast, and it is volatile.
It's big.
It's big. It's register memory inside a computer. And people are exploiting this for evil cyber attacker. People are exploiting this. So that's one of the projects I'm working on next year.
B is DRAM,
No, okay, we'll talk about that one. We'll get to that one.
I just remember the really silly looking capacitor.
This is flash. This is ROM.
Yeah.
These two, it's just the silly looking capacitor is the only thing that's different. Why don't we call this one DRAM?
Okay.
And the one with the silly looking capacitor, ferroelectric RAM.
I would just flip the coin.
Yeah,
Yeah.
that's basically what I did.
Yeah.
I'm not going to expect you to remember it because I don't remember it either.
Yeah, I just remember that that was basically what I just did as well in my head. That it's like one of them's DRAM.
Yes, and that's why I left those for last. Okay, different memory has different strengths, and this is the reason why we have the memory hierarchy in a computer. MRAM or ReRAM has the potential to replace all that memory hierarchy. SRAM is the fastest, but it is volatile. If you turn the power off, it goes away, and that's why it's a good puff. And it's huge. It's expensive. So we use this for cache. Fast, not a lot of it. Our next level of memory in a modern computing system is DRAM. And we use this for memory. It's our main computer memory for all the operations and things we're doing at that particular time. Not quite as fast as flash, but it does, you know. What?
You were saying the DRAM isn't as fast as flash?
Yeah. No, I'm sorry, not as fast as SRAM. The other thing I was talking about a few minutes ago, it's not quite as fast as SRAM.
Something didn't seem right.
Yeah, that was completely wrong. I know I said it. But you got high density here. You can store a lot of memory in a small space. It's relatively fast to access. We can't integrate it with a processor because it hates heat, and it is volatile. As soon as I turn my computer off, I have to reboot it and wait for all that memory to load before I can use it again.
It does actually say the read speed is as fast as Flash. I'm surprised that the Flash was slow. I mean, writing is way different. But
Well, this is like per bit effective,
yeah,
but at that 50 nanoseconds, you've got yourself a megabyte or something like that. It's not 50 nanoseconds per megabyte. It's 50 times 1 megabit. 50 nanoseconds. I can't talk today for some reason.
It's like how I can't spell anything.
50 nanoseconds times 1 megabit is the block of time that it actually takes to read it. But you get it at 50 nanoseconds per bit effectively. The big advantage here is it's non-volatile, which means I turn the power off and it stays. If we could get a non-volatile memory that was fast, that we can integrate with a processor, we'd have the one memory to rule them all, or the top of the pyramid in Dr. Cambo's slides.
RAM.
Yeah, ReRAM, MRAM.
So wow, so FRAM's slower writing than DRAM.
Yeah.
But it's
We're getting there, and it's not as dense either. I can't get as much memory in a small compact space. We started out, we really went into this memory array organization. We're gonna pack the memory in a 2D array. It's the most efficient way to do it. And then with Flash, we're gonna make it 3D. So we're just gonna stack chips on top of chips. But in the basic 2D memory structure, I've got these memory cells arranged in rows and columns. So I'm gonna need some addressing here to tell me which row I'm addressing, some address bits here, and then a decoder that goes into 2 to the n to address each individual row. And I need some column addresses and a column decoder here in the most basic circuit. These were a real pain to interface to because outside of a few chip control signals, you had to control the timing of the data and the addresses going into the chip. And if they weren't exactly spot on, it wouldn't work.
launch trial and error, I see.
Yeah, it was a lot of fine tuning your timing to get it to match up. And it wasn't like the MRAM array we're using right now. It's designed to have these 200 nanosecond or 20 nanosecond pulses going into it. Well, we can't do that with an Arduino or even with the Wi-Fi board. So we put in like 2 microsecond pulses, and it's forgiving enough to take that.
Yeah,
These old chips wouldn't do that.
yeah, actually, but I found the baud rate limit of Arduino.
Mhm.
9600.
Baud rate is different than bits per second. Baud rate is bit changes per second. So if you have a data stream that is like zeros for 8 clock cycles, and then it goes 1 for 8 clock cycles, that is still 1 baud that you've gotten through there.
Okay.
Yeah, as opposed to
But isn't
16
2600
bits.
Just the default, you could bring it up to like
No,
11,000.
I was able to
So-
actually get it any higher, and then I looked on Stack Overflow, and there was no solution to get it higher either.
So baud rate's faster than a 9600 baud rate will give you more bits per second than 9600.
It came with while I was doing my light sensors for Cambo's class, that it meant that I had to wave my light sensors around for an extended period of time.
Right. And again, we're talking about dial-up speeds. Okay. So slightly smarter chip. Not much.
Smarter by not much.
It's basically the same thing we just talked about. When we get to up into the later generations, I've got a controller in there that works a lot like a microprocessor. It's got registers that you have to set up to get it working in the right mode. and probably 800 pages of documentation associated with that. So you figure it out, or you get a professional to actually write a memory controller for you. You can get those, like on the Cordis board, there's DRAM on there. It's called SDRAM, which is DRAM that looks like static RAM. But it is DRAM, and you have to set up the control registers correctly, and there is a built-in controller in the Cordis board. And a lot of these controllers, even microprocessors and things like that, you can buy as components and put them in an FPGA. So you don't have to design everything yourself. You just hook it all together. That's what we're doing on the other project. The open digit line memory, we can pack things in a little bit tighter if we share a digit line contact between two cells. And this is what got us to that 6F squared memory. Yeah, this is, one of these is flipped. I've memorized this already.
Isn't it the digital?
This one, wait, this one should be going the other way. This one should be mirror imaged.
Squares on the left, circles on the right.
Right.
Yeah.
So that one's.
Okay. Open DRAM architecture, it had basically what we were doing, and this was kind of what we were doing on our project too, so this might make more sense to you at this point, is we had two separate memory arrays, and we were taking the digit line that had data on it from one memory array, and the digit line that was pre-charged to VCC over 2 from another part of the array, another subarray, and comparing them in the sense amp. That gave us a strong 0 or 1 on the output in order to make that work. I will grade your projects eventually. Yeah, I think that was on the calendar for tomorrow, or maybe I can do that on Monday. I can put it off even further. It's this not having a whole bunch of stuff to do that's taking me an infinite amount of time to do anything. It was more entertaining to sit and talk to Ben about random stuff and imagers today than it was to actually do work.
I was talking about the project really on Zoom.
Yeah.
How the Fowler engineer is nuclear.
It takes he wanted to know how much power it took to run the Aladdin array, and I just told him I have no idea, just kick in the auxiliary nuclear. No one ever measured that. It was horrible. Okay. It can be described as nuclear. This 1T1C cell, and you built this in your project, the capacitor goes to VCC over 2, so I can easily charge it and discharge it above that level. We have a word line, my row line. When I choose this row, this signal goes true, turning on that transistor, which dumps the charge off the capacitor into the bit line capacitance, which is much larger. And because of that charge sharing, even though this is charged up fully to VCC or 0, only goes up a little bit or goes down a little bit. So basically, I pre-charge the voltage to VCC over 2 with equilibriate. I turn on the word line, and my signal goes a little bit up or a little bit down. That's how I tell in your projects whether you're reading a 0 or reading a 1. Go ahead.
It does go low faster if you're reading a 0. You read a 0 faster than if you were to read a 1.
Yes, and it, cause see the transistor, as long as this word line is above a threshold voltage, that transistor will start to turn on, and even in sub-threshold, it's starting to turn on a little bit. So it's turning on about at this point, but it just takes a little bit longer for charge to move out than that little capacitor to suck charge in.
Yeah, and there's the issue that I ran into where half the time when I'm reading a 0, I write a 1.
Yeah.
Right now.
That's okay. Okay
and
then.
you had mentioned something about computer scientists write algorithms so that if your code is mostly 1s, it'll kind of flip it and make it mostly 0s.
Right.
Faster.
Yes.
Does that mean that your circuit waits for the system to settle less? If it's a 1 versus a 0?
It's more of a concern of power draw. It's going to affect the average power out of the systems, which means things will be run cooler and behave better.
Yeah.
And
you want to avoid as much heat as
right.
possible.
And I just say that as long as you give me a bit and tell me what the polarity is, I'll let my programmer figure it out. Details left to the reader. Nobody will want to work for me after this.
Especially with
No, that's fine, because I mean, if you're just starting out, you want to be the guy that just has to figure out whether it's a 0 or 1, and if it's flipping the bits or something like that. You don't want to be the one who's like doing all the system level stuff and figuring out the algorithms. You need people who've been around a little bit longer for that. So the charge sharing, and we talked about this a little bit, the M bit is much smaller than the digit line capacitance. So when I close the switch, the way we calculate this is we say Q initial equals Q final. Q equals CV. CV. So C digit on the charge on one side would be C digit times VCC over 2 plus whatever's on the M bit. Its voltage difference across that capacitor is whatever the cell voltage is minus VCC over 2. That's going to equal the final voltage, and the final voltage will be the same between both of them. So that is C digit times V final, C M bit times V final minus VCC2. And you do some algebra on this, and you can get the signal voltage. That's how much voltage you are going to raise or lower the VCC, the pre-charge value by, is V cell times C M bit over C M bit plus C digit. And we know C digit is much bigger, so this is a number is much less than V cell. Okay. And then our timing diagram got a little bit more complicated when we added the sense amp in. And this is what I was expecting to see on your projects. Is first you pre-charge the digit line to VCC over 2 with equilibriate. You turn the word line on, and my digit line voltage goes up a little bit because that charge. And then I turn NLAT on first, which means pulling it to ground, because it's the NLAT is the negative power supply for this latch. And then I turn ACT on a little bit later, and that's the positive power supply for the latch. And doing it in that order helps prevent latch up. It helps prevent latch up in your latch. Helps prevent your latch from going into linear mode. And so if I do that in the right order, then this little bit of a charge above it saying this is higher than VCC over 2, so it's going to pull the digit line all the way up to 1.
My waveform that sputtered to life.
Okay.
It wasn't entirely wrong.
Yeah, I'm amazed. I've spent half my life debugging circuits. I can sometimes look at them and figure out what's going on, and how big of an error you've got. Sometimes it would take me a while too. So when we're writing, what we're going to do is we're going to enable the write. So what we enable the write with that tri-state buffer, just like you did in the project, and you have to turn on the I/O transistors. And I told a lot of you to just make the write enable and the C select the same signal. So when I'm enabling my write, I turn on these transistors. If these transistors don't turn on, you can never write into that cell, because this is what takes the write signal and feeds it back into DOA and DOAN which actually connect to the memory array. Wow, see, this makes more sense this time now that you've actually done it. We can do it a lot faster. So here's the standard sense amp, and you implemented this in the project. And pretty much here we have the sense amp part, we have the equilibration part, we have these I/O lines, and the I/O lines decide whether this is connected back to DOA. So they're my throughput transistors. For the project, we had IOA star tied high, which meant that this part of the sense amp was always on, and we had this tied low. So this part of the sense amp was always off, and that just simplified things a little bit.
Is that why the B side didn't matter as much?
Yeah, the B side didn't really matter too much because we weren't using it.
Hmm.
If we wanted to, and normally this would be like hooking between two different arrays. If we were reading off side one, we would turn the ISO A on and we turn ISO B off. And if we're reading off of side two, then we turn ISO A off and ISO B on. I think I said that right. But for the project, you didn't have to go that far. So then, yeah, we get a more complicated timing diagram. This is the one from the midterm exam. You're equilibrating here. So when your equilibrate signal goes high, your digit line should go to VCC2. Some of you, it didn't quite make it. Some of your equilibrate circuits were slow for some reason. I turn word line on, and then the digit line comes up because that means we're reading a 1. And then as I turn the sense amp on, that 1 goes all the way up to VCC. When I'm writing, where's C select? C select comes on, and as C select comes on, I can actually write into the array and write a value onto D0. In this case, I'm writing D0 back down to 0, and then I start all over again. Why can I just look at your diagrams and tell what's going on? Because I spent most of my life as an engineer looking at imager timing diagrams like this. They're roughly the same. Looking at pedestal voltages, and pedestal voltages are kind of like that kickback charge when you get on D0. So yeah, they all make sense.
You've seen one imager timing diagram, you've seen them all.
You've seen one imager timing diagram or memory timing diagram, they all look amazingly the same. Okay, now there were certain voltages inside the array that we had to get above VCC, like the word line voltage. We had to get up to a higher voltage than our input voltage supply. So we had to have a driver for that was capable, a charge pump driver that was capable of producing a higher voltage. Again, a very linear, very analog circuit inside of this memory chip. Most signals have a high level just at VCC if we don't care about them. This was because of the dropping a threshold voltage problem across that DRAM chip, across that DRAM 1T transistor. So that DRAM 1T transistor loses a threshold. We want to get a full VCC on the capacitor because otherwise that tiny little capacitor cannot drive the digit line. Another issue we had to get some voltages below ground. We tied the body of the 1T transistor, if you have the 1T, 1C right here, the body of this transistor was actually tied to something I believe was called VBB, which was less than ground. And the reason we wanted a voltage less than ground is we want to actually have a body effect in this transistor, increase the threshold voltage so that the leakage current through this transistor is smaller. And leakage current in this transistor just means I'm dumping more charge off of that transistor, so I have to refresh more often. So it's cheaper just to put in another power supply.
Why don't we put more than VCC on the capacitor? It's that if we need the line as a whole to be VCC at the end of the sense amp pulls it up to
Right.
VCC so we can do our logic and stuff. If VCC was 1 volt normally, you have a 1 volt system, why don't we just put 5 volts on the capacitor, and then when you open up the transistor, then it equals out and you kind of get 1 volt on the line, and we can skip out the sense amp entirely.
You might be able to do that, but you probably couldn't go up as high as 5 volts. But maybe you might be able to go up like a VCC plus and then raise VCCP a little bit. You'd have to raise VCCP too.
Yeah.
And you'd have to do it in a way that doesn't stress the components.
Mhm.
5 volts might be a little bit too much,
Yeah, I think
but that might be a good idea because that would mean your sense amp would have to be less sensitive.
because you're at 5 volts, things
Yeah.
might start burning out.
Yeah. But if it was like 1.5 volts, you get that much more charge on the digit line.
Yeah,
And then you can make your sense amp smaller,
it means you need more charge pumps,
right?
but you don't have to put those directly next to things.
Right.
The sensor.
Yeah.
And the only issue with putting more charge pumps in it then is because then your overall circuit's bigger and then take up more space.
And you would need digit line drivers that were kind of custom too, but I'm sure those are too. So yeah, and I mean, it might be something, things like that, if you're working at Micron, it might be something worth looking at.
Mhm.
Or asking the question,
I just
maybe,
gotta work at Micron now.
no, somebody may have tried it before. And the thing is that's kind of a dangerous place to go to. If someone's tried it before and failed, that doesn't mean that it's a bad idea.
Mhm.
It just means you're going to get more resistance.
Well, this person may have tried it and failed, but what if we do it this way?
Yeah.
I don't really know how I could like design that and test that or simulate that.
You could simulate it
Yeah.
by just raising the digit line right voltage.
Because I'm not changing any of the components.
Right.
physically.
Yeah.
You can see what burns out and what doesn't.
You change the pulse source on the digit line driver.
Are things burning better graphics?
Unfortunately, no.
A little hard to tell, but
Multi-sim, they might have an animation where the part blows
I
up.
think, there's like a plugin you can download from Multisim that like lets it have like it has little snapping animation.
Oh, okay.
They're just like,
Yeah.
it's like this doesn't work.
Well, you can put LEDs and multi-sim that actually light up.
Ooh, yeah, it's pretty cool.
Yeah.
I'm testing things out.
Okay.
Multisim's actually really cool, especially
Yeah.
Multisim 14.2 is the newest one.
I don't know.
I was messing around with it in physics once.
Yeah. See, the physicists use it, and I use it.
I'm a little upset that the physicists have current going on in the wrong direction.
Does their multi-sim have current going in the wrong direction? Okay.
The
See, that shows that we're right.
The physicists do, and it's upsetting.
It upsets the physicist. Oh, darn.
Well, no, it upsets the electrical engineer that.
Says the one going to become a physicist.
Yeah, but I've learned to deal with it. I make more fun of programmers than I do physicists. Okay. Most NASA things and most of the I worked on soft money most of my life. The way these projects worked in NASA and for other places was that you had to have a scientist as the principal investigator on the project, meaning it was some NAMR or somebody like that. And then everybody who was doing the work was the co-PIs, like the engineers and the rest of us. So we got to, yeah. Generally, yeah. There's a lot of figureheads. We have the science goal, but we have no idea how to do it. Okay.
The spirit's there. But
The spirit,
the execution.
but the execution we need you guys for. Okay, so I always ultimately worked for planetary scientists, physicists, and NAMRs. NAMRs. That was the technician's pet name for them. Oh, yeah, right. We want, if you want to know, the disconnect between what I do and what the technicians do was at least I understood what they were doing. The NAMRs would come down and just say, "Work your magic" to the technicians, and they thought they were just.
That would be a fun band name, Julia the Noms.
Yeah. Oh, that was okay. Sorry. That was an actual band when I was at Auburn. Was Mr. Resistor and the Incapacitors. Okay. We want to generate those decode signals for the road decoders. Different ways we can do it. We looked at this in one of the homeworks. We could do a static decode tree. It's going to be the most power hungry and the biggest. We can do a pre-charge and evaluate. This is like dynamic logic. And we could use pass transistors. This is smaller, takes less power, not quite as reliable. And the P and E is only gives me good signals during half the clock cycle. So we looked at some different things there. We looked at some different architectures here. The open gave us a really small area for our 1T, 1C. The problem was we're taking data from one subarray and comparing it to pre-charge levels on the other half of the subarray, so they ended up being being noisy. We had to have a very good sense amp in order to make this work. So the next thing is they went to the folded. It had an 8F squared. It was a little bit larger unit cell, 1T, 1C part, and I could stack these every other row, but had much higher SNR. And then we went into the bi-level, which, and I think this is actually the bi-level right here. We went into the bi-level, which got us back to the 6F squared and still fixed the signal to noise problem, with the added benefit of we could twist wires in there in the bi-level. And that twisting helped increase the signal to noise ratio even more. This was a chart that was amazingly useful on the midterm exam. And that kind of just comparing the different architectures. And I'm sure, you know, you come up with something different, you know, and if it's better, people will use it. And if it's better and you can convince other people that it's better, that's the other part. This is why we work on presentation skills here. Tri-level plaid.
If you ask Vitaly, he'll try to make fifth dimensional travel plan.
Yeah, probably.
Yeah.
Fifth dimensional trial plaid, full-time travel.
There's no read time because it's already there when you go for it. It's traveled back in time.
Well, yeah, there were people at JPL that were doing stuff like that. I mean, and they had no. They had funding is the thing, and they would go through this presentation, and you're like completely wowed, and then suddenly it hits you, and I go, if you only have a transporter.
Oh God, we can't let Vitaly acquire funding, or else it'll be unstoppable.
If Vitaly ever gets funding, who knows what would happen. And you slip it over to Tom, our designated Yeley, and he's the one who raises his hand and just starts going into, do we want to work with these guys? Oh, sure, we have a transporter. Sorry. There are people who are funded to do things like that, blow bubbles in space and build ladders to the space station. Okay, so column decoders, again, we can go through that same type of thing. We can do a static decode tree. We can do pre-charge and evaluate. They all have their trade-offs and they all have their limitations. Static, it's size and power. The problem with P&E and pass transistor is noise margins, and but they're smaller, and power power dissipation. Okay. Redundancy. We've used this since the 256K generation. They found out their yield was going down as the arrays got larger. So what they did is stuck a few extra rows and columns on there.
That's such an engineering solution.
It is. I love this. This is the engineering solution. We just put a few extras on there, and if one of them's bad, that little microcontroller we built to control this memory anyways just says, okay, if I'm going to fire this address row, I really meant to fire this redundant row instead. And they've done this to like a real logical engineering conclusion, is if hackers want to look at my memory and see what's stored on there, I'm going to scramble the physical addresses relative to the logical addresses, so they have no idea what's on my array. They can't look at it anymore with a little IR camera. That
Don't just double debug.
Yeah, it's all gobbledygook because it's all in different orders. Once you start doing things like this, people will want to do it more. That's like an engineering law.
I would increase the use of the phrase
Gobbledygook.
gobbledygook because it's one of my favorite synonyms of nonsense.
Okay.
I hate to try to write that word out.
They've also done things where they've added like an entire, what they find at Micron all the time is that what usually happens is they get these large defects, like a speck of dust has plopped itself down on your array, and it just takes out a whole array or a whole region. So they also have gone to the point where they have redundant subarrays also. So they can replace out a whole subarray if somebody sneezed on it or something like that.
Oh no, sneeze on subarrays?
Well, that's why they don't allow people in the manufacturing line anymore.
Sneezing.
I had this whole view of the engineering line at Micron being like this little lab you could play in, like at JPL. And I got there and their engineering line was like this robotic masterpiece of engineering. It was beautiful.
It wasn't anything like Willy Wonka's chocolate factory.
It wasn't like Willy Wonka's chocolate factory. Sorry.
You know, my other
Nobody cares because you're not taking the final, are you? Okay. This is my last day to do this to you. I'm sorry.
No, I'm having a great time right now.
Ben's having fun. Zach's having fun. The rest of you guys are kind of quiet.
My other favorite synonym of nonsense along with gobbledygook is moon rings. When you're just looking at just miscellaneous like
Mood rings. I actually know.
moon runes.
Oh, moon runes. Okay.
Yeah, where you like look at some code, it's like it's like, I have no idea what this code is doing. What are these moon runes?
Okay. So something like that.
Most people just think Latin. Like this is Latin.
Mm-hmm. Convert everything to unary and just go away. And then it all makes sense. So another problem we have is that when we lay out the masks and everything, there's these edge effects where things aren't quite uniform around the edges. And you could actually physically see this with imagers. It looked like all these arrays had a picture frame around it. So what we did is we would not use those. We'd power up those rows and columns that were on the edge, but not use them in the actual image because they have slightly different this one has no rows next to it that are powered up, so it has a slightly different gain and everything, so it just looks funny. And you have to go about 3 rows in before those edge effects go away. And it's due to non-uniformities in the photolithography and also non-uniformities in the relative power around them. Things that are in here are going to be a little bit warmer than things out there and all that good stuff. Temperature effects. So we don't use that. Everything ultimately comes from a data pen, and we looked at those pads too. How much time do I have? So this data pen has to both handle data coming in and data coming out. If the data's coming in, it needs to go immediately be buffered, buffer everything. Put it in a multiplexer so it goes to the correct row and column through a write driver, and we implemented kind of like this part in our project and into the array. When I'm reading data out, it's got to go back off this way, go through a sense amp. There's a helper flip-flop here that helps kind of like pull it up a little bit before it gets to the sense amp. And another, oh no, that's the equilibration circuit. Well, that's in the sense amp. And the helper flip-flop helps to pull things up, and then it goes back out. I have to take this data, and I have to, coming from every possible bit in the array, and multiplex it back down to a single output buffer, buffer it again before I write it to the real world. That is the data path. We built a significant portion of this in the project. Okay, so the voltage regulator. Now, what we really want here is we want, if we have not quite enough power to power the chip, not quite enough voltage to power the chip, we want as much voltage out of it as we can. If we're in our operating voltage, we want a range, we want to keep the voltage fairly steady even if there's even if there's fluctuations in what the user is actually providing to us. The other piece there is when it goes back up again is for burn-in, because we want to be able to stress these chips before we send them out to the customer. Get rid of those infant mortality chips. I will be back in a minute. 34. If we don't get through this, nobody cares because